A short video of a textile worker fitting socks onto a metal form recently racked up nearly 200 million views on YouTube. When you watch footage like this, your immediate instinct is to assume someone in an editing room simply cranked up the playback speed. The sheer speed of the movement feels entirely unnatural. But the audio gives it away. This is real-time speed. We are so accustomed to thinking of factory robots as the apex of efficiency that we forget how quickly human hands can move. But this speed raises a significant biological problem. Without microchips or servos, a human nervous system attempting to process physical inputs and outputs at this frame rate should crash. To understand the biological engine powering global manufacturing, we need to drastically slow down time and look at exactly what happens inside a single 2-second loop. When we slow it down, we can see that a 2-second cycle of fitting a single sock actually contains dozens of distinct, highly coordinated microactions. If you or I tried to do this, our brains would have to consciously send individual sequential signals to our hands, grab the fabric, stretch it out, align it over the cylinder, pull it down. This illustrates motor chunking. Instead of processing a sequence, an expert's brain fuses separate commands into a single unified action block. This block bypasses the slower prefrontal cortex and routes the entire sequence through deeper, faster neural circuits. All hesitation vanishes. The mind executes the task like a piece of pre-compiled software code, rather than making active choices. Beyond the software of the mind, the body itself changes. Hitting a daily quota thousands of times a week triggers physical alterations within the nervous system. The worker's nervous system undergoes a biological mechanism known as myelination. In this cross-section, myelin acts as organic insulation. It wraps around nerve fibers, preventing signal leakage and accelerating transmission. This split-screen chart contrasts the sluggish speed of an unmyelinated nerve above with the hyperfast capability of a fully myelinated pathway below. The worker hasn't learned a trick. Their biological hardware now holds the industrial-scale bandwidth required to operate at this level. Zooming out from the internal neurology, we can look at the external biomechanics, specifically the trajectory of the worker's hands. There is a critical detail in their form. Between finishing one unit and starting the next, the worker's hands never return to a neutral resting position. This vector graphic maps the exact elliptical trajectory of the worker's motion. It shows a closed-loop momentum system where the kinetic energy from finishing one object perfectly positions the hand to begin the next. Eliminating the physical acceleration and deceleration things conserves massive amounts of energy. This prevents severe muscle fatigue over an 8 or 10-hour shift. Sustainable industrial speed requires eliminating the physical friction of starting and stopping. Returning to real-time speed, the perception shifts. Every rhythmic snap is the visible result of a human body physically synchronizing with the assembly line. The global economic driver that necessitates this extreme physical optimization comes down to piece rate pay structures in manufacturing. Workers are paid based on their exact output. The financial incentive to shave milliseconds off a cycle time directly dictates and molds human biomechanics on the assembly line. We tend to imagine that modern factories rely entirely on automated robotics, but in many sectors, human labor remains the most agile tool available. Behind the dopamine hit of a highly satisfying viral clip lies a sobering reality. The highest performance engine in many modern supply chains still operates on a human pulse.